The purpose of architectural sunlight design is to take measures to obtain appropriate and not excessive direct sunlight inside the room, according to different use requirements of the building. Sunshine refers to the phenomenon that the surface of an object is directly irradiated by sunlight. The numbers of sun exposure are expressed as sunshine duration. The maximum hours of sunshine at the same latitude are the same, but the actual sunshine hours are different due to the difference in coat cover and the time it blocks the sun. The percentage of actual sunshine hour and the maximum sunshine hour at the same time is called the sunshine rate. There are many beneficial effects of sunlight. The metabolism of living organisms can be promoted through photobiological reactions. The use of ultraviolet light can sterilize, prevent, and treat disease, using infrared radiation to heat and dry. Use of direct sunlight and shadows can enhance the three-dimensional effect of the building. However, excessive sunlight is unfavorable. It is easy to cause indoor overheating, resulting in increased energy consumption of air conditioners. Direct sunlight will cause glare, damage eyesight, and lead to produce failure and accidents. Working in an overheated and glare environment is easy to fatigue and produce efficiency. Direct sunlight will also cause damage to items, fading, deterioration, and explosion. Excessive exposure will endanger human health and cause disease. Therefore, the architectural sunshine design needs to consider the sunshine time and sunshine air, ensure the necessary sunshine, and avoid excessive sunlight entering the room, so as to take advantage of a favorable side of sunshine and control and prevent the unfavorable side of sunshine. Buildings with different functions have different requirements for sunlight. According to the different use of the building and local climate conditions, it is necessary to strive for sunlight or avoid sunlight. The buildings that need to strive for sunlight include ward buildings, kindergartens, greenhouse, residential buildings, etc. These buildings have different requirements for sunlight. Wards and children's activity rooms need sunlight around noon to get more ultraviolet rays, and agricultural sunrooms need all-day sunlight. In order to meet the needs of plant growth, residential buildings only need a certain period of sunshine to meet the needs of sanitary conditions and the use of solar radiation to increase room temperature. Buildings that need to avoid sunlight are roughly divided into two categories. One is to prevent indoor overheating, mainly referring to buildings in hot areas, workshops with high temperature operations, and rooms with constant temperature and humidity requirements. The other is to avoid glare and prevent chemical reactions, including exhibition halls, drawing rooms, reading rooms, precision machine workshops, and certain chemical plants, laboratories, processing plants, etc. Since the sun altitude angle and the sun azimuth angle are both needed in the seating design and the architectural sunshine design, next let's learn the calculation method of the altitude angle and the azimuth angle. The movement of the Earth around the sun according to a certain orbit is called the revolution. The time of one revolution is 1 year, and the orbital plane of the revolution is called the ecliptic plane. If the Earth's axis is inclined, it intersects with the ecliptic plane at an angle of about 66 degrees, 33 minutes. This angle of intersection and the inclination of the Earth's axis are fixed. So the range of direct sunlight varies periodically between 23 degrees 27 minutes, north and south latitudes, thus forming the 4 seasons. The solar declination angle is to describe the variation range of the direct sunlight hitting the Earth during the Earth's revolution. That is the central angle between the sun's rays and the Earth's equatorial plane, which represents different regions. From the equatorial plane, the north is positive and the south is negative. The range of the declination angle is positive and negative, 23 degrees 27 minutes. This is the solar declination angle for the main seasons of the year, and the solar declination angle varies in different seasons. There are different hour angles at different times, which are represented by omega. Since the Earth's revolution is 360 degrees in 24 hours, the hour angle per hour is 15 degrees. The hour angle ranges from 0 degree to 360 degrees. The time used in the sun sign design is the located average solar time, which is the time system that the sun is located at 12 noon due south, not standard time indicated by the daily logs. The incident when the local sun is located in the due south is 12 noon. The position of any observation point on the Earth is presented by the angle between the vertical line of the place and the equatorial plane. That is the geographic latitude phi. The latitude of the equator is 0. The northern hemisphere is the northern latitude, and the south hemisphere is the south latitude. Latitude ranges from 0 degree to 90 degrees. The position of the sun is expressed in terms of solar altitude and solar azimuth. The angle between the sun's ray and the ground plane is the solar altitude angle, expressed in HS. The angle between the projection line of the sun's rays on the ground plane and the south direction of the ground plane is the sun azimuth, which is presented by AS. As the Earth orbits the sun, the sun's rays at the same location change with time, resulting in a change in the solar altitude angle with time, 0 at sunrise and sunset, and maximum at moon. It can be seen from the figure that the sun latitude angle in the morning is HSA, the sun latitude angle at moon is HSB, and the latitude angle in the afternoon is HSC, all of which are positive values. Since the positions of the sun in the morning and afternoon are symmetrical about moon, HSA is equal to HSB. The solar azimuth angle is 0 with positive source, positive clockwise and negative counterclockwise. It can be seen from the figure that the azimuth in the morning is negative AS, and the azimuth in the afternoon is positive AS. Since the positions of the sun in the morning and afternoon are symmetrical about moon, the solar azimuth angle in the morning and afternoon are equal in value and opposite in sign. This is the formula for calculating the latitude and azimuth of the sun. Using the condition that the solar latitude angle is 0 at sunrise and sunset, the time of sunrise and sunset can be deduced, and the calculation of the solar azimuth angle can be simplified. Using the condition that the moon hour is 0, a simplified calculation of the moon day solar altitude angle can be derived. It can be seen from these formulas that there are only 3 factors that affect the solar latitude and azimuth, namely latitude, solar declination angle, and hour angle, where latitude represents the difference in location, solar declination angle represents seasonal changes, and hour angle represents a change in time. Next, let's do 3 exercises. Find the latitude and azimuth of the sun at 3 p.m. on the beginning of summer in the air of 35 degrees north latitude. It can be found from the beginning of summer that the declination angle is equal to 15 degrees, and the hour angle calculated from 3 p.m. is equal to 45 degrees. Substitute these values into the first and second formula respectively and found that the sine of the solar latitude angle is equal to 0.708. The solar attitude angle is 45 degrees 4 minutes. The cosine of the solar azimuth angle is equal to 0.255 and the solar azimuth angle is 75 degrees and 15 minutes. And the sunrise time, sunset time, and solar azimuth angle at the summer solstice in the year of 35 degrees north latitude. From the summer solstice, it is found that the declination angle is equal to 23 degrees 27 minutes, which is converted to 23.45 degrees. From the sunrise and sunset time, it can be known that the sun latitude angle is equal to 0 degrees. Substitute these values into the third and fourth formula respectively and find that the cosine of the narrow angle is equal to minus 0.3 and the narrow angle is equal to positive and negative 107 degrees 45 minutes. Turning 107 degrees 45 minutes clockwise and counterclockwise from the moon, or rotate by 15 degrees per hour. That is, the sunrise time is equal to 4:49 and the sunset time is equal to 19:11. Cosine of the sun's azimuth equal to minus 0.4858 and the azimuth equal to positive and negative 119 degrees 4 minutes. Then the azimuth angle at sunrise time is minus 119 degrees 4 minutes. The azimuth angle at sunset time is 119 degrees 4 minutes. Find the solar attitude angle at moon on the summer solstice at 23 degrees 8 minutes north latitude and 40 degrees north latitude. From the summer solstice, the declination angle is found to be equal to 23 degrees 27 minutes, which is converted to 23.45 degrees. It can be known from the moon time that the narrow angle is equal to 0 degrees. First, compare the latitude with the declination. The latitude in the year of 23 degrees 8 minutes north latitude is smaller than the declination, which needs to be calculated by the sixth formula. The latitude in the year of 20 degrees north latitude is greater than the declination and needs to be calculated by the fifth formula. Substitute these values into the sixth and fifth formula respectively to obtain the solar latitude angle of 89 degrees 41 minutes in the year of 23 degrees 8 minutes north latitude and 73 degrees 33 minutes in the year of 40 degrees north latitude. Did you find out the above calculations are not difficult, but each region needs to be calculated every day and every hour, and the amount of calculation is very large? How to simplify the calculation? You can also think about why the sunset standard is formulated according to the winter solstice and the big cold day. Does the overhang size of Beijing Siheyuan have anything to do with the altitude and azimuth of the sign?